you and my collaborators. Thank you for listening to this talk.
Thank you, Yannick, for this talk. Questions, please. I don't see any, so I'll start myself. Did I understand correctly that you measure the propulsion initially?
Yes.
You do not measure the position, do you?
No, we don't. This would be indeed possible, and you could also measure both the position and the self-proportion as a dual measurement. We found the sort of interesting new physics is contained in the self-proportion measurement only, which is why we focus on that case. Actually, your work from 2011 sort of elaborated already on the positional measurement.
But only for the passive case, right?
For the passive case, yeah. But the physics very much stays the same in the active case, so there's nothing new that comes in there.
Okay, David has a question.
Yeah, nice talk. I think in the passive case, you often find that feedback cooling is kind of the optimal extraction procedure. Can you talk at all about how that generalizes when you go to this active case and you now are measuring the velocity at the initial time?
Sorry, I'm not aware of feedback cooling. Can you elaborate?
Well, I guess just kind of, moving the trap so that the particle sits at the minimum of the trap. That's often a way to kind of maximally extract energy from it. But now that you have this velocity information, how does that sort of intuitively change the extraction strategy?
I mean, I'm not sure because I'm not aware of these strategies. But one thing I can say is that the protocols we find here are very much such that the particle does not sit at the center of the trap. So, like as Sarah also mentioned in her talk earlier, it's quite interesting to see how the particle sits at a certain sort of higher potential in the harmonic trap, in order to very delicately extract this work, which I think is also something which we don't fully understand exactly how it works. But it's quite crucial to not sit at the center of the trap. Yeah.
Thanks.
Yeah, are there any further questions? No? Well then, Yannick, thanks again. And we start with the next lightning talk by Trevor GrandPre from Princeton. Okay. Trevor,
hey,
can you say something? Yeah, we can hear you. Hi.
Okay, you can see the slides too, right?
You see the slides, we can hear you.
Perfect. So, well, thank you for allowing me to give this talk. Today, I'm going to talk about how you can infer irreversibility from time series data. Here's an example of time series data from neuronal activity, where each horizontal line is a specific single neuron, and if the spike is high enough, then to surpass some threshold, it's firing, and if otherwise it's not. And the idea is, can we infer irreversibility from this type of data, which of course has implications towards other systems. But first, let me just introduce, I guess, the motivation. So a lot of, but if we just think about equilibrium thermodynamics, we always want to calculate the free energy, but a lot of times this involves knowing a model of the Hamiltonian and the energies. But so I guess the motivation is, can you really infer a free energy in a different context by just particular looking at colloids? And if you knew the energies of these configurations, for instance, could you just infer the free energy without having to prescribe a form of the Hamiltonian? So this is similar to what I'm inspired to do for the entropy production rate. So let me just talk more about this system. So the neuronal activity that I mentioned was from a salamander retina, and they were shown grayscale images. And the idea is that in a small patch of the retina, they were simultaneously measuring 100 neurons. And that's what this data is. And the idea is you can binarize it, as I mentioned, where zeros is so each element is their state readout. So there's some measurement time, say 20 milliseconds, where you're asking whether or not you're above some threshold. And then you get so-called trajectory or word. And the idea is, what can this word tell us about the irreversibility and also the information content in this time series data. So there's been traditionally two main ways. One is by to measure the entropy reduction rate, which one is by taking the time derivative, of the Shannon entropy, and one of the terms will give you the entropy reduction rate, where Kij is the rate to go from J to I, and the probability distribution to be in state J, for instance, is Pj of t at time t. And the other picture is, of course, the trajectory picture, where you can ask what's the probability, where say C is some configuration of the system at the subscript I, and the idea is if you can follow this trajectory, what's the probability of taking this trajectory forward in time over the probability of taking the trajectory in reverse. And this is related to the entropy reduction rate as well when you take time to infinity. So there's the idea is we want to take that time series data and apply it to this ladder method. And this was first done by, I believe, by this PRL paper by Edgar Roldan and Juan Parando, so-called plug-in method. And there's many other methods, I would say here, that have been trying to infer irreversibility for systems without prescribing a dynamics for it. Here, I'm going to focus on this KL divergence, so I'm just mentioning this one. But yeah, this is the question. We want to infer irreversibility without trying to give a Langevin equation or a rate equation for how the neurons or the biophysics of the neurons. And so this is a caveat that I want to mention, is that I'm not trying to model all of the irreversibility of neurons, because of course they use a lot of energy. At one time they can use 20% of our body's fuel, even though they're only 2% by mass. A lot of this is for maintaining chemical gradients, such as sodium-potassium gradients for driving action potentials or packaging neurotransmitters into vesicles via proton gradients. So none of that is going to be in this coarse-grained binary sequence. So I'm not going to claim that this is the entropy reduction rate of single neurons, but instead it is a way to infer the arrow of time, because we know that when the entropy production rate is non-zero, this allows us to know whether time is going forward or backwards. But in the equilibrium, if the entropy production rate is zero, then you can't tell the difference between a movie of dynamics you're playing forward in time or backwards in times. So in this context, this is relevant to neurons because we know that our brain keeps track of time, and that's important for many reasons, like circadian rhythms, motor coordination, sensor processing, social interactions. And so this is a way to infer if single neurons have an arrow of time, which is relevant to this to our brain's function. So that's the question I want to answer, is like, we know that on a neural networks that at some the brain definitely dissipates energy, but is that like a collective phenomena, or is that do the single neurons have an arrow of time? Okay, so I'm going to talk a little bit about first this like plug-in method and like the new contributions that we've developed in this archive paper. But the idea is you can your total observation time is capital T, and the idea is that you can block or put into blocks your total trajectory, which of length k. So you fix k. Say like k could be words of length 4. So if you had something that's much longer than 4, you block it into 4, and where delta tau is how often you're measuring the state readout, and NW is the number of words you have from a single that once you block it into k. And the idea is just to give you an idea about how these words infer irreversibility. This would be an equilibrium word. This would be an equilibrium word. These are so-called palindromic because if you flip them, if you turn them around, they're the same word. And the same thing, well, this one is not a non-equilibrium word. This one's a non-equilibrium word. Okay, so the idea is that this is for k equals 4. And you can now carry this through to probability distribution. So the idea is we want to, from a trajectory, we want to empirically construct distributions. And so the idea is like, let's say capital N is the total amount of samples you have. And so the idea is the probability distribution of observing some word W is the number of times you see a particular word over the total number of samples. Given that you are asymptotically approaching, you have enough samples that, that it's asymptotically approaching the right answer. So on average, you'll get the right answer. But there's random errors in the distribution of words that that goes like this, this term here. And the idea is that now if you plug these statistics into the estimator for the KL divergence, then what we see is that random errors in the probability distribution of words turn into systematic errors in the KL divergence, where you have these terms that go A over N and B over N squared, which are corrections to the KL divergence at a particular time. So here, time is fixed, and all you're doing is increasing the number of samples that are going into your distribution of words. And so the idea is that, for instance, if you were to look at one, and we can actually calculate these coefficients. Well, in practice, we fit them. We just fit the 1 over n and 1 over n squared. But in principle, we can actually compute these coefficients. So, for instance, A is related. So omega prime here is just related to how many times do you see a word in the forward distribution, but it doesn't show up in the backwards distribution. And similarly, the second term is related to these distributions forward and reverse. And ideally, it's just because you're not seeing enough occurrences of these words to accurately make averages. And this will actually lead to an overestimate of the KL divergence. And so to estimate, show this point, I'm going to first show a two-state system, which we know is in equilibrium. And the idea is that you can, it doesn't matter what these rates are. In a closed two-state system, the entropy production rate has to be 0. And so here it's just running a simulation where we now showing that if we now just compute this KL divergence as a function of time, it actually, even after 1 million samples for just a two-state system, right here where the data stops, the answer is significantly non-zero just by plugging in the data and using this. So this is just showing that there's an expensive cost to be model-free of the dynamics. And where this is a fit, where the 0 is just a fit to the 1 over n and the 1 over n squared term that I mentioned in the previous slide. And in principle, I mentioned it's two states because if you have higher number of states, the number of samples you'll need will increase exponentially to converge this estimator. And so here's just now, let me show you a non-equilibrium example. So here, now we're changing. For each t, we're going to change t and increase the number of samples that we use for, these are already converged in the number of samples. Now we're just changing t to show that we get the exact entropy production rate for a three-state system. So here it's still Markov system, 3 states, but now the rates are such that it's non-equilibrium and there's cycles. And so this is just showing that for 2 different measurement readout, delta tau, that if delta tau is small enough, you can actually reproduce the exact entropy production rate, which is given by this black dotted line, showing that there's, of course, which is what we've known for a while, is that there's this 1 over t correction. So the idea is there's an order of limits. You have to take the number of samples to infinity first, and then you take the 1 over t. And so our contribution is that the sample in your estimate matters. So let me just lastly just show the actual data are now applied to neurons. So here we look at 100 neurons, and the idea is that we fix the segment to 10 words of length 10. And so let's look at the bigger plot first. The idea is the blue here is measure the KL divergence. And so there's over 100 that are non-zero, but the idea is we shuffled the data, and then that's the red. So it's showing that there's enough data here to get past the sample size limit, because if we shuffle the data, it's 0 within error bars, and it's non-zero in the blue. So there is information within these neuronal activity for single neurons. And in the inset here, it's just showing that if you actually plot it for, this is K pretty much, so words of length 2 to 8, there's not much irreversibility, but as you go past 8, then you see a burst of sort of irreversibility and information content being shown on length scales or time scales of 40 milliseconds to 200 milliseconds, which actually is relevant to perception. So with that, I'd like to end and say that so we have a model-free estimator that has systematic errors in both samples and duration. But if you account for those errors, you can, in principle, get back the exact value. I know there's some caveats here with coarse graining and partial information, but in principle, there are cases where you can get back the exact. And when we apply this to neural data, we see that even individual neurons have a significant non-zero irreversibility measure. And I'd like to thank my collaborators and my funding sources, and also a small shout out that I'll be starting my group at WashU in the fall doing more work. So stay tuned.